WhatsApp group, the Telegram group. Be a member of Tamil Nadu Science Forum. So Tamil Nadu Science Forum was formed in 1980s by few research scholars, including Dr. T.R.G., Dr. Murugan, who are doing PhD in nuclear physics department at Madras University. Since then, the organization has grown into a state-level organization. Initially, it was confined to have lectures, hall meetings in universities and colleges. They discuss only the physics, and they go beyond physics and move around, and they cover all science topics because they feel that the interdisciplinary knowledge is very much essential for all researchers. So initially they conducted hall meetings. After some time, they thought that the meetings has to be taken to the local level and people.
Interactive.
They go to
I can take
streets and those days they prepared the films and show the slides, camera, the projectors and slides also, and creating awareness among the people in the local area. In 1986, they started the science Jata. It started from Kanyakumari to Chennai. For 15 days, they roam around and come to Chennai and have a huge meeting. So Science Forum was introduced to entire Tamil Nadu. It became a state-level organization. In 1997, we launched a magazine called Tulip. This is for the children's magazine. And from 1987, since then, it was continuously we are publishing on monthly basis. It is without any advertisement. The beauty is the magazine doesn't have any advertisement. It is a self-supporting magazine. And in 1991, we started another magazine called Jantar Mantar. It's meant for the college level students. It's in English. Thereby the publication becomes second activities. Initially, it starts with the science communication, and later it goes to the science publication. And third, we thought that the participation level of the level is confined to one particular gender. So we thought that no, see, including women and participation in women is very less. We started a separate group called Samam, which is meant for bringing more women into the STEM. That's the third activity which has been launched in 1993. Since then, a lot of women participation has been increased. Then we have another division called Science for Youth. Young people should come to the science. That's the fourth activity. Apart from fourth activities, we have two more activities. One is development and environment and development. Both should go together. We need a development, but simultaneously should not spoil the environment. So both should go together. We have a separate group working on environment and development. And the fifth one is the health and education. Sixth one is the health and education. Now education and health are separated. We have 7 different groups operating within Tamil Nadu Science Forum. So if any of you are interested to participate in any of those activities, if you are interested in science writing, you can be working on the science publication. If you are interested in the environment and development, you come here and do a lot of things. We have a lot of problems. This year, the Children's Science Congress. Now we are organizing Children's Science Congress at the age of the level of grade 8 to grade 10. We throw a project to them, and the students will do an independent analysis, and finally they submit a project report. We have a competition on district level and state level competition. Initially, we used to have the national level competition. Now it has stopped, and it is up to we go up to the state level. In this year, the theme of the research is the water resources and environment. So it's going to be an so we have a lot of opportunities to work on the Tamil Nadu Science Forum, and we continue our journey with the science communication. PSL is part of the science communication, and it was doing only in school level. It was started in 2018. Let us focus on the higher level science as well. So first lecture was organized in the same library in 2018. That was a Stephen Hawking Memorial Lecture. It was first delivered by Dr. T.R.G. It's a Stephen Hawking Memorial Lecture. Now it is the 93rd lecture. So I expect, then after some time now, a couple of months back, we started doing the science lectures in Tamil as well. Makkal Ariviyal Soppozhivu. Now it is the 13th lecture going on. It's going to be a 23rd. In 29th, we have a lecture on the NASA. Many of you have heard about the advanced satellite which has been launched a couple of months back, NASA. We have a lecture on NASA, both English and Tamil. And we also have a plan to have a lecture on the advancement in remote sensing. That's going to be happening in September. So there are exciting things which is going to happen. With this, let me start my introduction of Tamil Nadu Science Forum. I invite Dr. K.G. to introduce the speaker.
Hello, everybody. Thank you very much. I'm going to introduce the speaker. This talk is about 10 years of gravitational wave astronomy. Now, the first thing is gravitational wave was predicted about 100 years back by Albert Einstein. He proposed a theory for gravity, which is called general theory of relativity. And it is beyond what Newton gave 400 years back. He said that apple fall because of gravity. Moon also goes around, which is called universal gravitational law, which was given about 400 years back. And that was not sufficient. And we have to go beyond that, was what was predicted by Albert Einstein in 1915. And it makes corrections to Newton's theory also. And it makes profound changes in the way we do that, our sciences. And for example, without general relativity, your GPS, which you are having in your phone here, will not work properly. If you say that the time at, say, New York now, as expected, will be different from what you expect if you don't use the general theory of relativity. So this is a very, very important change. Your GPS will work. It is used, for example, in your Google GPS map that you have. You see various people. In fact, you say location share. And you put the location here. Somebody is staying in, say, Anna Library, is what is shown in your friend or relative's phone. It will not show Anna Library if GPS does not use general relativity. It will show that somewhere near Cancer Institute you are there. It may be good for you or it may be bad for you also. So these are the things which have changed with the theory of general theory of relativity. And Einstein, with his profound new theory, made enormous change in our way of thinking about science. So that is as far as the general theory of relativity is concerned. Now, the general theory of relativity predicted gravitational wave, which essentially means, as you know, probably, gravity is a very, very weak force. Thank God. Otherwise, all of us will collapse into ball. That's all, because all of us will attract each other through gravity. And that attraction is going to be very, very small. And that is thing. And that's also playing the role between sun and earth, etc. On the other hand, if some big object, what you call black holes, with masses of the order of 30 times the solar sun's mass. I don't know how many of you know what is the mass of sun. It is 10 to the power 30 kilograms. So this is a kind of mass you have 30 times that. If two of them collide and merge together, there will be enormous energy released. And that energy released will shake the whole universe to some extent. And if you happen to be in the neighborhood, you are dead already. There's no problem. But it comes to us. And in fact, it changes the distance between you and me by a small amount. What is the amount it is changing? It is changing by a so small amount. It is in the thing is like 10 to the power minus 20 centimeters. It's much, much less than the size of the nucleus. Okay? We are That kind of a thing, we have reached a level that we can measure such changes. It's an enormous technological advancement which has happened in the last 30, 40 years. Unfortunately, in our schools and colleges, etc., we still talk about only Newtonian theory. We have not even graduated to this thing. And this kind of popular science lectures is supposed to provide at least some enthusiasm, interest in the modern developments which are taking place. And we have been organizing this from 2018 onwards. We have come to the 93rd lecture, and we could do it even during COVID by online. And that's one thing just changed our perspective also. We are organizing this lecture as I speak. It's also available in YouTube. It's also available in Zoom. Anyone who has the Zoom link can also see. And the good thing is, initially it was meant for the Madras city residents, and that's how our halls were full. In fact, the first talk which I gave was held at the ground floor, and in the ground floor there are about 300 people attending. So I have never had such audience. So this is a kind of a thing, but with Zoom and YouTube, many people, even within Madras city, would come here and people will join from YouTube, Zoom, etc. So this is the thing. The next thing is about K.G.Arun. K.G.Arun is a great friend of mine. In fact, when Srinivasan was asking me about this, I asked him, why don't you ask Arun to speak? Because he's an expert on gravitational waves. He's been working on the projects associated LIGO and Indian LIGO also now. And they have been that distance, smart distance measurement. He has a contribution in that whole thing. There are thousands of people, and he's one of those people who were involved in the instrumentation and development analysis. Various parts are there. The number of scientists involved are more than 1,000 people, and he's one of them all over the world. And from India, at least from right, about 50 to 60 people were involved.
40.
Huh?
48.
48 to be exact. So this is the thing, and they did a lot of analysis. And the number of such mergers of huge black holes, masses of 30 solar masses, 40 solar masses, 100 solar masses, etc. There are several now in the past 10 years have come of the order of hundreds of them have been discovered so far. And it is actually, in the scientific community, it is shaking our interest. And this is one of those areas where new things will happen and various interdisciplinary activities will take place. And computer and computational work, of huge computational work, it may happen even artificial intelligence, machine learning, all those things will start playing a role. So you have to be careful about it. So please be aware of the changes. Otherwise, you will stay with Newton and you have to go beyond Newton. Youngsters particularly should learn about these things and understand what is happening and have a clear idea. K.G.Arun is from Chennai Mathematical Institute, where I was also there for about 10 years. And he is an expert on gravitational waves. He has been working, and he is also associated with the Indian LIGO project. And he is also, in younger days, also indulged in doing some work for Kerala Shastra Sahitya Parishad, which is inspired our work also. And with many other friends, he was also a member of that. And he is interested in popularizing science. He gives several lectures through Chennai Mathematical Institute and other places. And it's a great opportunity for us. And this is a kind of a thing which is very difficult to get a person like him to come and do this kind of a thing. He has been kind enough to agree to our program. And I now invite, without much ado, Professor K.G.Arun to give his talk. Thank you.
Yeah, thank you, TRG, and thank you for all of you for turning up on a Saturday morning. Yeah, it's great to be here. My first visit here, though I've gone through the road many times. So as was mentioned, I'll be talking about the last decade, which has been very eventful in astronomy, especially where we used gravitational waves as an astronomical tool. to learn many things about the universe. So this is going to be like an overview of what has happened over the 10 years, starting with a longer introduction as to what are gravitational waves and why should we be excited about them, and what lies in the future in the years and decades to come. So as I mentioned, so this is. Okay, no, it takes a while. So as I mentioned, this is the reason that the first discovery of gravitational waves happened almost a decade ago on 14th September 2015. And this is, I'm showing you a signal. I'll come to the details in a minute. And so this is a good time to look back after 10 years to see what we have learned and what lies in the future, which is the reason for this lecture. Okay, so the outline roughly is going to be that I'm going to introduce gravitational waves to you without going to any mathematical details. I will tell you why they are unique and how they can complement the standard, telescopes and so on. And and I will also talk about what kind of new astrophysics gravitational waves can enable, and talk about where we lie today and what is the scope in India, for example, and also internationally in the next couple of decades, for example. Okay, so this is a picture of our galaxy taken from some mountain in the US, and this is showing you not just our galaxy. There are several stars and star clusters, planets, etc., which will be here. So this is typically how we look at the universe. And how we look at the universe is, the question is, how do we learn about them? So there are various means by which we learn. Predominantly, it is through light in various electromagnetic bands, starting from gamma ray all the way up to the radio. But we also see them, at least the nearby universe, by using particles. I mean, it can be neutrinos, it can be cosmic rays, etc., which is also been there, though we cannot see them far away due to their weakness. But I'm going to talk about a new kind of way of looking at the universe, which is through gravitational waves, and I'll tell you why we are excited and how it complements the standard ways of using the other tools to understand the universe. Okay, shouldn't go that far. So this is a picture about various electromagnetic telescopes which range from gamma ray up to radio. Some of them are on the ground and some of them are in the space. And we observe various phenomena in the universe by these telescopes in X-rays, gamma rays, etc., and understand what happens in some remote corners of the universe. And so, this contains many. I think there is no Indian one. There are several Indian ones also. Though this picture doesn't have any any of them. So this is how we typically look at the universe and understand kind of what happens in the universe. And most of our understanding of the universe has come from using electromagnetic waves. So it's good to keep that in mind. Okay, so now I'm going to talk about a new way of looking at gravitational waves. It is using gravitational, new way of looking at the cosmos or the universe using gravitational waves, and I will tell you why it should be exciting. I can use this one. No, it's okay. I'll do. Next. Okay, so as K.G.Arun was already mentioning about the shift in understanding gravitation from the early eras of Isaac Newton to Einstein. So Einstein argued that if you think about space and time as a single entity, and then you introduce mass or gravity into it, he kind of if you have a rubber sheet which is like this flat space-time in the absence of any matter, if you put matter, they will be bending or curving, which you can see depending upon the mass. You can see the more massive ones will curve more, and the less massive ones will curve less. And you can think of the effect of gravity on the space-time to be to curve or bend the space-time. Then you can ask the question that suppose things are dynamical or accelerating, for example, two planets going around each other or two stars going around each other, you would expect that they are going to, when they go around, they're going to send out ripples in this space-time. Very naively speaking, at the very basic crude level, that is exactly what are gravitational waves. What I'm showing you is like a binary star system or a binary black hole system, which I'll come to, which is dynamical. So they go around each other, and then that sends out ripples in the curvature of space-time, which is, in the simplest terms, that is what a gravitational wave is. Can I go to the next slide? Okay, So just to summarize the properties, it is generated by accelerating masses, very similar to electromagnetic waves, which are generated by accelerating charges. So it's an analogous thing. It is represent the space-time curvature, and it is also transverse, at least in Einstein's theory. That means whenever a wave is going by, the effect of the passing wave is felt on a screen or plane orthogonal to the propagation of gravitational waves. And in Einstein's theory, they also travel at the speed of light. So just like light, gravitational waves also speed with the same speed as light. Now, if you know electromagnetism, if you're taking a course, you would know that electromagnetic waves are dipolar. You talk about dipolar oscillations, but unlike electromagnetic waves, these are quadrupolar. So if you do not know what is a quadrupole and so on, do not worry. But if you know and compare dipole to dipole and quadrupole, you can say that there is no dipolar gravitational waves in GR. It is at the leading over a quadrupole. I mean, I'll come to that maybe in a minute. To the second part. If you don't know, you can forget it completely. Can you go to the next slide? Yeah. So the important thing now is that you need only gravity. They're messengers of gravity. So any object that is gravitating and is can give you gravitational waves, even if it doesn't emit light. So this gives us a completely new way of probing darker side of the universe. Dark in the sense which doesn't emit in light. Even then, we can use these waves, and which when we detect to probe those dark phenomena, which are normally not seen using electromagnetic telescope. That is extremely important to keep in mind. Can you go to the next slide? So now let's understand what is the effect of a gravitational wave. So I'm arranging a ring of small test masses here, and my wave is going orthogonal to the plane of the screen. So what it does is to, as the wave, this is a waveform. You can see that the amplitude goes up and down. It is going to set this test particles into motion. As you can see, it gets first, in the first cycle, it gets elongated. That means squeezed in one direction, stretched along the vertical to get to an ellipse like this. When it comes back, it again goes back to the circular one. On the other cycle, it goes and kind of stretches in the orthogonal direction. That is, it stretches in the horizontal direction and squeezes in the vertical direction. It again goes back to the circle and so on. So as the wave kind of goes by, you can see that the ring of particle gets stretched and squeezed, and that is the effect that we are trying to detect. Now, if I want to say how strong is the passing gravitational wave, the best way to measure it is that suppose my original length was L, that is L here, and because of the gravitational wave passing by, this is now become changed by some amount. I will call that delta L. And if I define a ratio of the change in length due to the passing gravitational waves to the original length, that is this is a dimensionless quantity because this both length. This is called a gravitational wave strain. And when the strain is high, you can imagine that when delta L is large for a given L, it is going to be a stronger signal and vice versa. So we use this notion of dimensionless strain as a way to quantify the strength of a passing gravitational wave. Okay, now according to, you can compute gravitational waveforms in Einstein's theory. I'm not going to any details and so on. But if you look into the kind of features, qualitative features, if I look into a source, any source, it's got a mass m, and which is at far away at a distance of d, and has got a size or radius of r. Okay, so now the strength or the strain that I mentioned depends upon m by d, which is understandable. If it's more massive, it will be emitting stronger after gravity. And it also depends upon compactness. So what I mean by compactness is that if you have the same mass spread over thousands of kilometers, and the same mass is compressed to 5 or 10 kilometers, the second one, that is a compact thing, and when m by r is very high, when the object is very compact, the gravitational wave strength becomes kind of increased proportional to the compactness. So that means you need not only, things will of course emit gravitational waves, anything that is dynamical, but for gravitational waves to have a higher strength, you need compact objects moving at very high speeds. So this is extremely important to keep in mind that though our planets, and even if I do anything dynamical with my hand, of course it gives you gravitational waves, but they're too weak, and there is no hope of detecting anything. So if you want to detect anything on Earth with our existing technology, you need things which are compact, and that restricts our attention to certain kind of stars which are compact enough, whose signals we can detect. Okay, can you go next slide? Okay, so that, as I mentioned, that will bring our attention to two classes majorly. One is the neutron star. So if you, very naively speaking, as the name indicates, these are stars composed mostly of neutrons, and this is this is like one solar mass, that is mass of sun composed of neutrons is compressed to 10 kilometers. So that is how strong it is, because it's like a size of a city, and whereas sun's radius is 1,000 kilometers or more. So this extremely compact object, and these are both end products of stars. When a star undergoes, when a star shines at some stage, when it exhausts its fuel, it explodes, and after the explosion, you end up with many kind of end products, and the two of when the more massive stars will end up either as a neutron star or a black hole, and that is what we are after. Okay, so we can think of binaries, as I mentioned, consisting of two black holes, two neutron stars, or one neutron star and a black hole. So these are, I'll call this binary black hole, this binary neutron star, and the neutron star black hole. These objects, when they go around each other, just like Sun-Earth system, but replaced by these compact objects, you can, they emit gravitational waves which are strong enough to be detected on Earth by our existing technology. Can you go to the next slide? Okay, so now what did I say? Suppose I make a terrestrial source with 1 ton dumbbell separated by 2 meters, which is I can do, and I make it go at a speed of 1,000 cycles in a second with a frequency of 1 kilohertz. The kind of if you look at the gravitational waves produced far away from the source, the typical H that you get is 10 raised to minus 39. That is 1 by 1 and 39 zeros. Right? So it's going to be extremely tiny. And if I suppose I look into 2 test particles separated by 1 kilometer, the typical delta L that that is passing gravitational waves is going to displace 2 test particles separated by 1 kilometer by 10 raised to minus 36 meter. So extremely tiny that we cannot be seeing that. So it is almost hopeless with our current technology to think of detecting any gravitational waves that we can we can produce on Earth. Next slide. So if you replace this with an astrophysical setting, suppose I have 2 black holes which go around each other at a reasonable distance of 100 megaparsec, then delta L by L improves by 28 orders of magnitude. It becomes 10 raised to minus 21. And then if I have 2 test particles separated by 1 kilometer, this delta L, the separation due to a passing wave, becomes 10 raised to minus 18 meter. This still is 1 by 1,000 of Fermi, as TRG was mentioning. However, our technology has now advanced that we can detect such tiny displacements due to a passing gravitational waves, and that is what exactly LIGO does. Okay, so we are LIGO is trying to detect, it's a detector that tries to detect displacements of the order of 1 by 1,000 of a Fermi, or the size of the atomic nucleus. Can we go to slide? So these are the detectors which I mentioned. 2 LIGO detectors are in the US, which is like you can see it's a LIGO picture. This is 4 kilometer arm length. So you know that when we have a wide separation, your delta L by L, when the L is large, your delta L is high. So that is what you want. So this is 4 kilometer long arm length, and there are like 4 of them. So two in the US, 1 in Europe, and 1 in Japan. These are the ones which are operating currently with varying sensitivity. On LIGO is the most sensitive one, and there is one LIGO India here, which is in the planned thing. So we are going to build a LIGO in India in the next 5-6 years. I'll come to that in the second half of my talk. So how gravitational waves are detected is by using this kilometer scale interferometer. So interferometer, I don't know if you're an MSc student, may have done some experiments with interferometry on your tabletop. So these are like extensions of that to which uses the laser to monitor the end mirrors and tiny displacement that are produced. We use that but at a very large scale. So it's quite a big challenge to build a detector like that and maintain it and operate, improve the sensitivity and so on. But that's what a LIGO detector would do. Can you go next slide? So just to give an outline, so this is what LIGO does is the laser beam that is coming in. There's a beam splitter. It splits beam into the 2 arms, the 2 L-shaped ones. They go hit the mirror and come back, and this will come back. This will interfere here, and the interference pattern is observed at the photodiode. So when suppose you lock the interferometer, that means you can always lock the interferometer in such a way that you get a dark fringe, because you have seen, what is the interference pattern like. So you can initially lock the interferometer, but once a gravitational wave is going by, it is going to displace these mirrors, right? So from a dark fringe to which you had locked, you are now going to see some output at the photodiode, and this output diode should contain information about the passing source. So that is basically the way that's the way LIGO works. I'm going to show you more like a video how it is going to look. Can I go to the next slide, please? Just once more. Yeah. So this is exactly what I showed you. This is a beam splitter. This thing is coming. When a wave is going by, the end mirrors are going to shake, and you get this interference pattern here. Now, if you go to a wave thing, so this is a laser light wave that is going by. It is going and end mirror and gets reflected back. The other one also comes back after getting reflected, and they interfere here. When they interfere, you initially adjust it so that they cancel. So there's a dark fringe at the photodiode. But once the gravitational wave passes by, end mirrors are going to shake slightly. So you can see that the interference pattern is no longer, it is not completely cancelled. You do get some light. When you look into it, when you are off, you get dark fringe. But when the end mirrors oscillate, you get a bright fringe, and that is how this is what is used in terms of the method to detect gravitational waves. Now, of course, the only thing that can shake the mirror is not a gravitational wave. There are so many things. It can be starting from our ground vibrations to a flight going by to many things can do the same thing to it. So the challenge for an experimentalist and data analysis person is to separate out this noise and make sure that whatever you detect are indeed gravitational waves and not some flight going over your head. Or a car going by, or anything. It can be earthquakes actually can unlock the thing, because earthquakes remotely can actually so the interferometers are kept off for some time before it recovers and so on. So so many tiny things can lead to the same thing. So we need to have an idea about where they contribute, at what frequencies they contribute, and whether the signal we detected are indeed standing above all these noises, what we call as noises. Can you go to the next slide? Yeah, now I'm going to show you how the gravitational wave signal looks like. I'm going to show you a solution to Einstein's equation on a supercomputer. That is what this plot is. I'm going to show you the animation where two black holes go around each other. These things will show you the strength of gravitational field, and the gravitational waveform will come here as I play the video. Can you play the video, please? So these are two black holes, and you can see that the red one shows you the black hole has a strong field. They come extremely they're just going around each other. Initially, they emit like a sinusoidal, like harmonic thing, almost a sinusoidal thing so there's it goes on very slowly. These are very early stages of the evolution. But so you can see that as they go around each other, they lose energy. That is why they come closer. As they come closer, they emit stronger because gravity is higher. So it's like a runaway process, which starts at a very slow process initially. But as they come closer, you can see that they become more and more relativistic, or they move faster. By the time they come close to each other, they are almost at the relativistic speed. So when they come closer, like here, they just hit each other. This is a new black hole formed by the merger, and this kind of sheds away the thing and so on. Can you go to the next slide? Yeah, so this is what is seen. So you have two black holes which are orbiting around each other, loses energy due to gravitational waves, which bring them closer. When they bring closer, they emit stronger, and this runaway process leads to them merging or forming a single black hole. This transformation of two initial black holes to one final black hole is what we are hoping to see, and this is what LIGO has been hoping to see for decades. And after decades of upgrades and so on, there was an initial LIGO which was operating until 2007. Which was shut down for upgrade, and 2010 advanced LIGO, next version of LIGO, started to be built. And in 2014, when the new advanced LIGO was ready to be operational, almost, we're doing some kind of commissioning runs and so on, this event hit us. So this is the signal that we detected, which was just one day before we were actually prepared to start science quality runs. And this is, so as the name indicates, this happened on 15/09/14, which means 2015, September 14th is when it happened. We saw two black holes that was kind of orbiting initially, the late stages, when they hit each other and they formed a single black hole, and then there is nothing after a single black hole is formed, right? So, and as you can see that when they come closer, your amplitude increases because they emit strongly, frequency increases because they're going faster and faster around each other. So if you make a time frequency map, how the frequency increases as a function of time, and this is showing you the energy emitted in each one, you will see it's like a chirp signal. It's called you can fit, it's like a signal which increases as a function of time, the time frequency evolution as a function of time. And typically the frequency at which they merge is around 200 things. So it is interesting that if you basic filtering, if you put in the gravitational wave data into a speaker, you can actually hear this noise and a signal which will go up. I'm not showing you that, but I've shown you so many times I'm bored of it. But the frequency of these waves are in the audio band. So in that sense, it also complements the visible, the electromagnetic waves are like visible universe. And in that sense, gravitational waves is like an audible universe. You can just hear the murmurs of the universe in some sense. So this was the signal we had detected the merger of two black holes, which hit the LIGO detector, two LIGO detectors, because as I told you, you need to be sure about the noise sources. So if you have two geographically separated LIGO detectors, they are good in characterizing and ruling out noises to be sure of your detection. So it's very important. So can you go to the next slide? No, this is dependent upon the mass. For this masses is 230. It can be at 10. It can be at when you have binary neutron stars merging, it can be at 1000 hertz. But they all, and I'm saying 10 hertz to 10,000 hertz is the frequency where LIGO can detect. They all happen in the audible band, is what I meant. So this is for this system only. This, of course, it's a very short signal. The peak frequency is at 200 hertz. It can, it is sweeping through the thing. I'll show you another. When I go to binary neutron star, and I'll show you the long time frequency map which would come. Okay. So it is for this signal. So what we found was that it is it is a merger of 35 times the mass of sun, as TR was referring to, with another black hole with 30 times the mass of sun, which produced a new black hole weighing 62 times mass of sun. That means the difference, 65 minus 62, 3 times the mass of sun into c square is gone in gravitational waves. Okay, so that is the kind of energy that is released at 450 megaparsec. And of course, so much of energy is released, as PRG was mentioning. Gravity is weak, therefore it is very difficult to detect it. Even the energy is there. To tap in that energy, is very challenging because of the weakness or intrinsic weakness of gravity as a field. So for this detection and this discovery, these three gentlemen, Ray Weiss, Barry Barish, and Kip Thorne, got a Nobel Prize in 2017 for physics. And as TRG mentioned, there were significant contributions from 40-odd people from India to various things, and historically also in terms of developing waveform models, data analysis techniques, and so on, and also on the analysis of this event. There are significant contributions from several Indian researchers. So this is like a formal kind of arrival of a new cosmic messenger called gravitational waves, which can now be used, because now we can observe binary black hole mergers in the universe using gravitational waves and understand their properties and ask how they are distributed, what are their properties, etc., etc. So it's a new kind of way to probe the dark universe in kind of some sense. Can you go to the next slide, please? Yeah, please interrupt me at any stage. I should have been close. So I'm not going to talk about every event that we detected, 100 more than 100 events, as TRG mentioned. I'm going to talk about some exceptional events which had some kind of uniqueness. In 2017, after by then we had detected a few more handful of black holes, like 6 or 7. 2017, we had a very interesting thing. We detected a binary neutron star merger. Now, black holes are objects which cannot emit any light, because everything things cannot escape black hole. But unlike black holes, neutron stars can emit light. And when you see mergers of neutron stars, you expect gravitational waves, of course, but you also expect light. So that was the first instance where we saw both light and gravitational waves from the same source. It's interesting because it's like getting audible perspective from gravitational waves and visible perspective from the light that we receive. Can you go to the next slide? So this is called so this is again showing you time frequency map, and I think this would have merged at around 1200 hertz, not 230, because it's a low mass system. So this is showing you the time frequency map, how the frequency evolves as a function of time. This is where it merged, and this is all LIGO data. And if you go to Fermi, which is a space-based gamma ray telescope, after 2 seconds after this ended, Fermi detected a gamma ray burst or gamma ray flash there. And this is a well-known phenomenon. Gamma ray bursts have been detected since 60s. And we did not know what exactly is causing the short duration burst. So the burst duration in the gamma rays was also 2 seconds. So the short duration gamma ray bursts were conjectured to be due to mergers of neutron stars, but there was no way to confirm, right? So it was for the first time that we were detecting the merger of two neutron stars. And roughly after 2 seconds, we were seeing another gamma ray burst from the same source, which again lasted for 2 seconds. So we were confirming the long-standing hypothesis that mergers of two neutron stars can be responsible for a gamma ray burst.
Two neutrons are producing a black hole, or
yeah, so it is likely to produce a black hole, but there is no way to confirm it anyway because we do not have sensitivity in the high frequency thing. So typically, if you want to account for the energetics of the gamma burst, it should be a black hole plus an accretion disk. I'll show you kind of animation, but there is no way of scientifically confirming it because of our sensitivity is very poor in the high frequency.
So neutron star we can see.
Right. Yeah, so the components we can see, and mergers has produced something very compact, actually very likely black hole. Whether it led to intermediate more massive neutron star, then collapsed and so on, we cannot make statements with our sensitivity currently.
And these collisions are long drawn out of fast.
Long?
I mean, these are long drawn out. It's not happening.
No, so I think this emission goes on for millions of years, but we are seeing the last 20 seconds or 40 seconds with our detectors because it's a very weak effect. So we can see the late stages when it's strong is what we can see. But as you rightly said, it's been going on for millions of years, very likely. That again, we don't know, man, how million, is it million or billion? We don't know because there is no way of going back. And I mean, we have some astrophysical models will tell you that it could be millions of years, but there is no way. We are seeing only the late stages, the last few seconds.
Final death.
Yeah, the death, the last cry and the death, if you want to.
The gamma burst indicated.
So yeah, so I think I'll show you. I can explain. Can you go to the next one? Yeah, just play the animation, please. Yeah, so this is the animation of two neutron stars that come close to each other, and they merge. They merge, and as K.G.Arun mentioned, I believe they formed a black hole, but I cannot confirm. So this is formed, and now it gives you like there's a jet that is launched from the black hole. This jet is going through interstellar medium, which accelerates particles and so on. That is what gives you the gamma ray flash, and that is what we saw. So after the merger leads to formation of a black hole and then an accretion disk of some sort. From which it accretes, it launches a jet along the thing, and it gives you it, and that is responsible for the gamma ray burst, which lasts for 2 seconds. And of course, gamma ray burst lasts for 2 seconds, but we saw emissions in various bands of the frequency spectrum after that. X-ray, optical, and all the way up to radio and so on. So this, as the jet goes through the interstellar medium, it becomes weaker and weaker, meaning less relativistic. They give emissions, but the main emission, the prompt emission, is what I refer to as 2-second long gamma ray burst, which we believe is due to it's consistent with the astrophysical understanding that the merger of two neutron stars giving you a black hole and an accretion disk and launching a jet. That's what I meant. Okay, so this like animation there. So this first binary neutron star merger we saw a few more, at least 1 or 2 more of them, but they didn't have any electromagnetic counterparts because the jets, as you see, is a very narrow conical jet. So only if the jets are pointing towards us, we can detect them. So if they direct in some other direction, we won't be able to see that. So we at least had a 1 more confident detection later on, but that didn't give you any gamma ray burst. That's that doesn't say anything. But we were fortunate for this event to be accompanied by electromagnetic counterpart. Can you go to the next slide, please? So as I mentioned, this was observed in various bands. So in fact, this is according to Wikipedia, probably one of the most observed event in electromagnetic band. So at some stage after this event, like one day, almost every telescope on Earth was pointing to one galaxy in the sky, which is just to kind of following up this on various kind of bands. So it's a very extensively followed up thing. And scientifically, it did solve several of improved understanding of gamma ray burst, and again, threw many surprises as to what could be happening. I won't be going into this until there are questions at the end. Can you go to the next slide, please? Okay, so then the next thing was another important thing we found. So in the first case, we are 30 and 35, they're comparable masses within the error bus. But then we on 2019, April 12, we found an asymmetric black hole merger. Can you go to the next slide? So what we saw is that we found a merger of a 30 solar mass black hole with another 8 solar mass black hole, and it gave you 37 solar mass remnant. That is the final black hole that is found. So it is important because it was because I told you earlier that gravitational waves are dominantly quadrupolar in nature, But it is not the only one. As you go to relativistic, when you go to relativistic speed, there'll be subdominant, small corrections to it, and you can get octupole, hexadecupole, and so on. Again, if you're if you know multiple expansion, you would know what I'm talking about. So these are beyond quadrupole emission that we expect to happen. And because of the asymmetry of the system, we did detect this octupole radiation. Second thing is about the clear evidence for spin precision. So what happens is that, so you have two black holes going around each other. And so there's an angular momentum vector of the orbit and spin vectors of the black hole. So if they're all aligned, there is no problem. They all go smoothly. But if the spins are not aligned with respect to the orbital angular momentum, then what can happen is like, this is a atomic spectroscopy, right? You can have the spins, individual spins will start precessing around the total orbital angle. J is L plus S1 plus S2. So L and S vectors will precess around the J vector, which will give you, so what that means is in the waveform that we observe, you're going to see features which will account for this kind of modulations. So for the first time, can you go to the next slide? I show the animation. Yeah, you just play that. So if you have an asymmetric black hole system, I told you there are two things. One is spin-induced precession due to this S vector going around the one. So you can see that and due to the octopolar radiation, the radiation pattern of the system is more complex than what we have seen in the past. So again, it has many combinations. It has octopole on the one hand. It also has got the periodic modulation, which are not so visible, but of course, if you do a data analysis thing, you can extract them. So this showing one simulation that was kind of set to that. So you can see that this kind of thing is very important, because when there is more structure in the data or more features in the data, it helps you understand these binaries better, and that's what we want. We want to have a clear understanding of what is happening and where are they formed, etc., etc. So this is a very unique event in the sense of the new features that we had not witnessed until then. So after that, we did witness something with a mass ratio of 10, that is, like 14 and 3 kind of system. But this is the first one where we are seeing high asymmetry mass ratio of the order of 4 in this case. Okay, can you go to the next slide? Just just play that video, please. Yeah, so this is what I meant, that if you have black hole spin which are not aligned with respect to the orbital angular momentum, it can give you. So I'm showing you the waveform here. You can see that there are like amplitude modulation, phase modulation, and so on of this. So this vector, all these vectors sort of slowly go around. What that means is that, so the L vector, which is what defines the plane of the orbit, when the L vector starts precessing around J, the orbit is going to tilt, right? It's going to tilt. So you can see that this kind of these are the radiation pattern, and it gives you features which are like oscillatory on amplitude. The envelope of this thing will start showing oscillatory features and so on.
Like a top.
Like a top, exactly like a top. Okay, so that gets a kick, and that is not part of this. I'll not talk about the kick. Can you go to the next slide, please? Okay, so then you would be asking, now we have seen binary black holes and binary neutron star. Where is the neutron star black hole? Yeah, we did found one in 2021 January 15th, which is a merger of a neutron star black hole binary. And this is interesting because neutron star black hole binaries are believed to be existing, but even using electromagnetic waves, there was no confirmed, it is not easy to detect them in radio due to various reasons. So for the first time, this observation confirmed that there exist binaries which are mixed binaries consisting of a neutron star and a black hole. Can you go to the next slide, please? Yeah, so this is again, there were two events on 5th and 15th, and which confirmed the existence of this class of binaries which are believed to be there, but we are not seen in any way earlier there. So I think, of course, another thing is, ideally you can also get light from neutron star black hole mergers, because neutron star has matter, and when they merge, it can disrupt, it can give you the gamma ray burst like phenomenon. But we did not see anything here, which we believe is due to the high mass ratio. When the mass ratio, that is the mass, when the mass of the black hole is much larger than the mass of the neutron star, it just, the black hole just eats up the neutron star, and it gives no time to disrupt and so on. So we are yet to see a neutron star black hole merger with an electromagnetic counterpart, which is one of our top thing to be yet to be discovered. But it is interesting that we did see this class of system as well. Can you go to the next slide? And this is more recent. This was announced in this July, though happened in 2023, November 23. We found the mergers of two massive black holes. Can you go to the next slide, please? So what we saw is like a total mass of the black hole was in the 190 to 260 range within error bar. So it like 230, you want to take it. Can you go to the next one? Yeah, so what we saw is, roughly speaking, merger of 137 times the mass of Sun black hole, merging with 103 times the mass of Sun. So you can see that now the black holes, we are now confirming that black holes can exist in this 13700 kind of thing. I mean, we don't know how they are, are they coming from stars or are they coming from some other mechanism? We don't know. But this, anything about 100 solar mass, we call it to be intermediate mass because it's not like tens of solar masses. So this was the first confirmation, confident confirmation about black holes existing in this kind of very high mass end of the spectrum. And we believe this is not due to stellar explosion. It may have been a, so if you, we found that first black hole gave you a merger of 62 solar mass. If this black hole merges with another black hole, you can like double the thing, right? It is called hierarchical merger, where one black hole remnant merges with another black hole and this process goes on. So this kind of hierarchical merger is supposedly responsible for this kind of very high masses. And this is implications. The question is that how can we grow black holes from stellar mass all the way up to millions of solar mass is the question, which is an open question in astronomy today, as we have various types of data. But this is interesting that we found something, at least on the higher end of our spectrum, which is 100 to 200, that kind of range. Okay, can you next slide? Okay, so this is like my selected exceptional events that we had detected. And now I'm going to talk about where we stand with respect to these events and what we hope to do in the next few things. So this is showing you the, K.G.Arun was asking about the latest numbers. So these are observing runs of LIGO. The first one was detected in O1, first observing run. Then we had O2, second observing run. O3 had 2 parts. O4 has 3 parts. And we are right now taking data as we speak. We are in O4C, the third part of the 4th observing run of LIGO. And what is shown here is the sensitivity. So this is the noise, this is a noise background, how thing is. And you want, so if you want to detect system, you want to suppress your noise to higher extent. So as you go from O1 to O5, and O5 is in the future, but O4, for example, we improve the sensitivity by going down in this in the space of this curve. Right. So as we improve sensitivity, you can see that the number of events we detected in the first 2 observing runs were like handful, but O3 had significantly improved sensitivity, which led to hundreds of events. And O4, so O3 had around 89 candidates, and O4 even now, of 290, we have seen 200 more sources just in one observing run compared to all observing runs so far. That is because our sensitivity is improving. We are detecting more and more black holes of all types. So like every week, there is a couple of events which we have to analyze. So it becomes, it's now, we need to analyze and kind of report all of them. And so on. So it's interesting that we have seen at least 290 compact binaries, of which most of them are binary black holes. There's a handful of them are binary neutron stars and neutron star black holes so far. So we are in a kind of era where we are very routinely detecting binary black holes, and therefore we'll be using that to probe astrophysical aspects. Can you go to the next slide, please? Okay, if you want to look into the mass of the black hole, it's called a stellar graveyard plot. So these are the masses of black holes that we have detected. So you can see, so these blue ones are the LIGO detected black holes. This A plus B giving C kind of stuff. You can see, and you can see something. This is something on the higher end. This an old plot. It should now have gone above that. This is a kind of old one. You can compare that with, for example, electromagnetic detected black hole. So when black holes in our galaxy, for example, could be accreting gas onto it. When they accrete gas, they give you X-ray, and there are evidence for mass estimation based on this mechanism. But you can see that they are all on the lower end, 10 to 20 kind of thing. And we are detecting black holes by a different mechanism, and we can go up to 200, 300, and so on. So we have detected more than 100 now. They are mostly binary black holes, and this the length of the the list is still growing as we speak, and these black holes that we detected compared to the standard ones are extremely different from in terms of the properties, which means that we are probing them at a different kind of epoch or different kind of formation, etc. Can you go next slide, please? Okay, this is a quick one-slide summary of the science we have done. I think it requires a separate talk in itself. So we, of course, have taken a census of compact binaries in the universe, where they lie, how far they lie, what are the properties, are they precessing, are they spinning, are they non-spinning, and so on. One thing which I did not tell you is that because Einstein's theory has given its properties of gravitational waves, we can ask the question that given a gravitational wave signal, is it consistent with the Einstein's prediction? Right? So we can test Einstein's GR using gravitational waves, and we have done it on all these events, and we find no significant deviation from Einstein's prediction. That doesn't mean tomorrow we will not see. Our sensitivity is now at a regime where we cannot see. Maybe there is, maybe there isn't, we don't know. But so far there is no threat to GR. Then we have also seen, using the joint observations of a neutron star, light, and gravitational waves, we could also talk about Hubble constant, which is one parameter which governs how quickly the universe is expanding. Again, I did not go into the detail, but we can do this kind of measurements as well. And we also, and since we detected neutron stars, we can talk about the structure of the, what is the equational state, what is the composition of neutron stars. This we can ask, and we have answered that question also. And also I mentioned about gamma ray burst and jets in gamma ray burst. There are many interesting aspects of astrophysical jets that we learned by observing this 17 even that I mentioned. And of course, we continue to look for new classes of sources. It could be supernova in our galaxy. It can be something which we don't know, etc. So this is a new tool to look for any kind of source that emits in gravitational waves. Can we go to the next slide, please? Okay, now going towards the future, I mentioned about LIGO India. So this is called LIGO Observatory, which is going to be set up in Hingoli near in Maharashtra. So this is an engineering drawing, how once LIGO India is operational, this would look like this. And it got a DAE sanction on May 2023. And we expect to complete it by 2030, April 30th. So which is of course an ambitious plan and so on. So this would be like a new LIGO India detector, new LIGO detector on the Indian soil, and which will be built in collaboration with the LIGO lab, that's in collaboration with the US things and so on. Can you go next slide, please? So once we have that, we will have a geographically well separated LIGO and Virgo observatories, which will be operating as a global network, taking data by the multiple time, and this is exactly the kind of future in the next 1 decade or so, where we will be having multiple detectors taking data, routinely detecting these waves, characterizing them, and learning more about the universe and this phenomenon through these gravitational waves. Next slide. Okay, one more. So, kind of talking about the future, there are planned upgrades to LIGO, advanced LIGO, because advanced LIGO can be upgraded, but that's a considerable upgrade. NSF is considering an American version of what is called Cosmic Explorer, which will be like, which will be sampling. It's a next generation detector, which can sample 1,000 times the volume that LIGO is currently sampling. It may, depending upon the funding, which these days nobody wants to talk about. This can be, the plan is to have something started in the mid next decade. But again, it's subject to. And when this slide was given, it was, it is a different era altogether. But we are still hopeful that this funding can come, and we will build the next generation gravitational detectors. And a similar thing called in the European equivalent thing is called Einstein telescope, which will be upgraded to Virgo, which again will have comparable kind of sensitivity to that of Cosmic Explorer. So together we'll be going far out into the distance. We are seeing now nearby universe. Can you go to the next slide, please? Yeah, so we can, we'll be going too far out into the thing, and we'll be, probing very high redshift or very early universe when the stars were formed, or early stars and so on. So that will be interesting, because we are not, we are seeing this kind of this far away universe only in electromagnetic waves, and whether gravitational waves are showing you some surprise is something which will be interesting to see. So this, this will require you the next generation detectors to probe the early universe in the sense as early as you can go with this kind of things. Okay. Can you go to the next slide, please? The next more funded, more kind of solid plan is called space-based detector. This space-based detector will not be observing in the hertz to kilohertz band; it will be millihertz detector. Yeah, and it is funded, and this building is going on by ESA. Then this will be up in space by 2035, 3235, and it's funded, and things are going on. There is no uncertainty except for kind of in a technical thing they face. So this is going to be 3 satellites which will be separated by 2.5 million kilometer in space, and they will be going around the Earth's orbit. They'll be in millihertz, which would mean that instead of detecting black holes with mass of 100 or 10 or 100 solar mass, they'll be observing millions of solar mass black holes. So these million solar mass black holes are believed to be at the centers of our galaxy. And that is true. This recent Nobel Prize confirmed that at the center of our galaxy, there is something like as much as 1 million. If these black holes, when they merge, they will be emitting not in this the LIGO band, they'll be in the millihertz band. And the LISA detector is like is going to be probing these mergers of supermassive black hole in the next decade. Can you go to the next slide? One more. So this is showing you the orbit, how this is LISA orbit. LISA is going to go around Sun and trailing behind Earth, and it's just going to do these things because there are modulations which are these things you can localize the source in the sky and so on. This is showing you the LISA orbit in the sky. I don't want to go into too much of details, but I want to tell you that it's a very ambitious thing. Started in early 90s and so on. Now funded and is ready to. Not ready to fly, but it'll be almost ready to fly in the next sometime in the next decade. Can you go to the next slide? Okay, so now because just like in the case of electromagnetic waves, we have seen gamma rays all the way up to radio and so on. We are now going to have an equivalent thing. We are going to have LIGO-like observatories in this band, the LISA observatory here in the millihertz band, and this is something which I did not talk about. This is a nanohertz detector, which are called pulsar timing array, which is already they are taking data, they have reasonably confident about a signal and so on, but they will improve in the next decade. So you'll be having all of them. And if you go to very early universe, the early universe will give you gravitational waves in the in this extremely low frequency band, which is going to be going to the entire spectrum. So we are hoping that in the next decade we are going to see all of them. And can you go one step? So in kind of you can see that there is an interesting gap here between the ground-based detector and the LISA. There is a decihertz detector, which has got interesting thing between say 10 raised to -1 hertz to say 100 hertz. This kind of band in between. So there is some interest in the Indian community to build a decihertz detector, and this is showing you our theoretical sensitivity curves, how it will be, and there is some. I mean, we are something sent to ISRO already. ISRO is looking into it, but it's too early to say anything. But hoping that things go well. We may also, in parallel, I don't need to say there's a planned Chinese mission also in this band, which we don't know much about. But it's going to be interesting that if India can also increase its footprint onto the gravitational wave thing on the decihertz detector, it will have its own unique science, which I did not go into, and so on. So it'll be kind of interesting. Next decade is going to be interesting because we are going to have gravitational waves being observed by multiple frequency bands, and again, as I told you, they give you complementary probe to the universe compared to electromagnetic waves, and yeah, it's going to be a very exciting time in the next decade. Okay, can you go to the next slide? Okay, so I will conclude now. I hope I did not exceed the time. So I told you that gravitational waves give you a whole new way of probing the universe and solving the cosmic puzzles. Then existing generation of gravitational waves are improving sensitivity, and I showed you where we stand with respect to them and what we have detected. The plant and the next generation detectors will enable early universe probes, going to the first stars, for example. And the space-based LISA mission will be launched sometime next decade. And the hope is that we can convince funding agency ISRO that we also need a kind of decihertz mission and starts to kind of plan things around that. But that again is a question mark, so I'm not. I cannot commit. But with that, I think I'll stop and I'll be happy to talk to you and take your question. Thank you so much. Sorry.
Hello. So it's an exciting. We are talking about billions of light, such things. And, same time, locally we are concerned about its national politics, international politics, whether somebody will fund it or will not fund it. It's also nice. To the first scale, they are very, very tiny. It's very tiny. These 100 solar masses, 100 times bigger than sun. Yeah. Thousands of eggs can be fitted inside one sun. Think of hundreds of suns. So this is a way, and the numbers are mind-boggling. The concern by scientific community is about those things. We have reached that kind of level itself is very interesting. Now, floor is available for some question answer sessions. You can ask question in Tamil also. He can understand, but he will answer it in English. But if you feel like you can ask questions in English, please raise your hand. I'll just coordinate. One minute. So Reddy is giving a gift.
Thank you, sir. Thank you, sir. So I learned then. It's a good chance.
Okay. So now, yes, please. Go ahead.
Yeah.
So good afternoon, Arun sir. It is really a pleasure meeting you. So sir, I would like to ask a very important question that what do you say? You have told us that when two black holes collide actually, we're actually measuring how much intensity they are actually providing us, that is 230 hertz or 1000 hertz. Now tell me, how will we understand that how long before they actually happen? Because how will we calculate the time scale is my important question.
Yeah, so you're asking when was it formed, right? So you're asking about the, I mean, so we see the merging now. How many years in past was it formed, right? So I think this is something which we, unless we get emission from that side, we can only estimate. So we believe that if it is a typical time for it from birth to the merger, will depend upon the initials, how widely they were formed and how closely they were formed. So unfortunately, there is no way of directly estimating them. We have to rely on astrophysical models. For example, there can be models of stars which will tell you that, given this parameter, it may have been formed at this regime and so on. So, but they're indirect estimates, and right now we don't have any way of estimating when exactly it was formed. It can be only indirect kind of inferences.
Okay, sir. Now another thing is 1 minute. So now you have told me that when these two black holes are merging, some of the energy is actually dissipating. We thought that 6 solar masses have been. So have you observed any curve in this? Like if these many are colliding, then definitely this much energy will be lost. So do you have any Gaussian curve or any kind of curve which predicts how much solar mass will be lost?
Yeah, so I think I showed you the animation, which is a numerical simulation. So those kind of simulations have a unique prediction. If we know the initial mass and spin of the two black holes, Einstein's theory of relativity will tell you what is the final mass and spin.
Okay.
So what we estimate them is consistent with what Einstein's theory predicts.
Okay, sir.
So that's
Understood. Thank you.
That was it.
Yes. Yes.
Check. So, is it the same way that we are actually detecting something like some electromagnetic waves? Because what we don't know the exact nature of a gravity wave.
Hmm.
So are we only measuring the disturbance in the mirrors?
Hmm.
which is why we don't know what the actual source is, and we have to eliminate through data analysis so many different options.
Yeah.
So, so is it this? It's not in the same nature.
Yeah, so you're asking about how do we infer the properties
Yeah.
from a wave? Yeah. So I told you the output of a detector is the photodiode's output, right? The voltage will be fed in. That's the only input. That's our data, right?
We are only measuring disturbance.
Disturbance in the form of
wave that comes, right?
yeah. So in the form of a so what we record is the output of the photodiode, which is a combination of all these things there. That is the data that is given to us to analyze. Now, what we know is that from Einstein's theory, we know how the waveform looks like. What is the shape of the waveform that looks like? We make the best use of Einstein's theory prediction, and you use that to analyze the data. So we ask the question: is there any of the Einstein's theory predicted waveform fit this data within the error bars? So it's a data analysis problem that you're talking about, which is of course important, and also ruling out the obvious noises. So in that sense, we start with the raw data of the photodiode output and use theoretical models based on Einstein's theory to analyze the data.
And are these waves directional?
Yeah.
How do you know from?
Yeah, so I think so. Only one detector you cannot say, but if you have three detectors, it will be if it's coming one thing, it will hit one detector first and then the other one next. So you can do sky localization by triangulation, which is why we want more detectors across the globe, which will increase our ability to localize the source in the sky.
Okay, I have a couple of questions if there are no. Go ahead.
Since you were mentioning the importance of triangulation, does it mean that right now there is some kind of a coexisting observation going on between various LIGOs?
Yes, so I think I mean, as we speak, two LIGO detectors and the Virgo detector is operating. Virgo has less sensitivity, but they do simultaneously take the data and they do exchange data. And whenever there's an event, we do a joint analysis to see and make use of the information to know which part of the source sky the source is coming from. The LIGO detectors are comparable sensitivity, so that is easy, but Virgo sensitivity currently is less. So it's not adding too much, but yeah, you're right that we need to, we analyze. So this is a joint LIGO Virgo Kagra group of people, which now spans 2,000 scientists. We are kind of engaged in this analysis, joint analysis of the data, and that is how we do this thing. So all data is analyzed in conjunction with other detector data.
Just one other thing, we are now restricting ourselves to binary stellar systems.
Yes.
Are there any other kind of models which may emanate gravitational wave transformation?
So I think we are not restricting our sources so far has been only binary black holes and binary neutron stars. As you rightly said, suppose the star explodes, right? So that again will give you gravitational waves. But unfortunately, the strength is much less compared to binary. So we can detect only if it happens in our inner galaxy, for example. But the probability of a supernova explosion in our galaxy is 1 in 100 years. So, I mean, of course, it has been like 50 years now since the last one happened. So maybe we are up for a surprise anytime, but we can definitely detect a supernova explosion of the type you mentioned if it happens nearby. But that again kind of depends upon luck. The other thing is, suppose you are a neutron star and suppose something is falling into the neutron star, accretion of neutron star, that again will give you gravitational waves. But now that again is weak. So there are some sources which we now analyze constantly. But as we analyze them for years, maybe we can detect something from them. But right now, our sensitivity is not good enough, and the signal strength is not high enough that we are able to make any detection. But I agree with you, but the detector doesn't care about any of these things. So the data is analyzed subject to different sources and their physical thing. And we have found only binary black holes so far is the statement, but we will be sprung up for surprises in the coming years.
So since it's a rare event like a supernova, how much earlier can we predict with our current scientific technique?
No, we can't. I think so. The last one which happened in our galaxy was in 1987, which was a very big event. And I think since then we are not seeing anything in our galaxy. And our understanding of the rate is also not very high because due to various things. So it's a very rough estimate that it could be once in century, but it may be 200 years or it could be it can happen any time from now. So I think it's uncertain. That is true with every rate models and all the binary black hole rate models and so on about how many events will you detect was surprised. We didn't expect to detect so many events like 5 years, maybe 20 years back when I was doing a PhD. It was like 1 in a year, 2 in a year was the kind of best estimate of some time. So now we are seeing hundreds of events in a year. So our astrophysical understanding could be wrong either way. It could be too good or too bad. We don't know where we are with respect to supernova. So that's a fun part too in some sense.
Thank
I
you.
think this is because of the fact that we are detecting. Is it because of we are detecting events very far away?
Yeah.
Whereas in the case of neutron star explosion,
Yeah, exactly.
it has to be localized in the sense it's only.
Yes. So because if you think was supernova explosion, the strength will depend upon how asymmetric is the collapse, the explosion, and that that's very weak. I mean, compared to what we know of. So we can detect them only nearby. As you rightly said, we are going to 100 megaparsec, 3 gigaparsec, and so on. So number of events in that volume is higher, and that's why we detect more of the binary black holes compared to the neutrons, compared to the supernova or even accreting neutron stars.
There are some disagreements in the value of the Hubble's constant measure.
Yeah.
For us. So
Yeah.
how would your measurement?
Yeah, I think unfortunately so we did, and so there were Planck measurement and supernova measurement. Our measurement fell right in the middle. So with a very long tail, with kind of neither confirming nor ruling out as of now. But as we go further, we may have some ability to confirm, or maybe we may have a new estimate of Hubble constant, which will be another tension to deal with. I don't know which one will that be. Right? So, yeah, we are not in a position to. We have estimate, but it is consistent with both of them.
Slide 36. What is the y-axis? Slide 36. I mean, you actually 36.
No, sorry.
Is it the displacement of the mirrors?
Which plot are you talking about?
This one, the one on the right.
This one.
On the right.
Here, yeah. So this is the sensitive. So this is the Sn of f. So this is the Fourier transform of the 2-point correlation function of the noise thing. It is, in some sense, it's telling you the the power in the noise. We detect the noise, we know what are the noises, so we can characterize how much. How much is the power. So that is why we need to suppress it to very smaller and smaller values. So it's like, in some sense, it's a detector noise power that is on the y-axis.
And in one of the slides, slide 25, you said there are several puzzles related to GRBs.
Yeah. Yeah, so I think there are several puzzles. First of all, our understanding of GRBs. There are two classes of GRBs. One is the long and the short, kind of short GRBs. But GRBs are gamma ray bursts. So I think one thing is about the structure and geometry of the jet. So the merger will give you a jet. What is the structure of the jet? Is it like isotropic? If you take it, is it a homogeneous jet or not, and so on. So these are things which will require. So joint observations is what will be facilitating those kind of things. For example, we also don't know how does the mass of the mass of the neutron star, whether all GRBs will, all mergers will launch a jet or not. We are not sure. And that's the first thing, right? Then it's about the nature of the jet. We know nothing about the nature of the jet because we see electromagnetic emission far away from the source. So by combining gravitational waves and electromagnetic waves, we are hoping that we can bridge this gap and try to solve some of the thing. But the basic question is we don't know whether what fraction of these mergers give you GRBs is not known. And that will require more of the things.
You say that the GRB is transmitting in a specific direction.
Yes.
How can you detect it?
Exactly. So we have to be fortunate, and our detected sample should be high enough to kind of do any good job. That's why second binary neutron star merger we did not see any kind of GRB, but we don't know whether is it because it didn't launch a jet or we didn't see the jet. That is the thing to be solved. So we need to have a higher thing to make any statements, supplemented with the numerical analytical modeling of GRBs and so on.
Good afternoon, sir. How do we estimate the masses of the two black holes or two neutrons colliding?
Yeah, so I think I showed you the waveform, right? So I think I didn't go to the data analysis thing. So let's take this one. So now, depending upon the, so we are observing it from F1 to F2, some frequency band, right? Now, the depending upon the mass and the spin of the black hole, the waveform will be different. So what we do is that we have a data there, and we do a cross correlation of various waveform models which spans different masses and mass and spins with the data. Then we ask the question, which of these waveform models fit the best to the data, and that is how we detect. So what we do is we got a bank of waveforms which will have different masses, spins in some grid kind of thing. We cross correlate them with the data and infer what is the best fit one, and we take that. It's, I mean, we do it a bit more detailed thing, but that is how we do. Depending upon the mass, spin orientation, and so on, the waveforms are different, which is what is used to infer like inverse reverse engineering problem.
Yes, sir. And the model you shown are two-dimensional space.
Which models?
Sorry, every model that space-time rubber sheet you tell us.
So I think that is for just showing.
Yes,
Yeah,
sir.
just to explain. I don't know how to draw a four-dimensional thing, right? So yeah, I mean, I agree with you. It's a very toy thing to kind of explain to, not to you, but not to people like you, and like more of a general
Okay,
public
sir.
audience.
Yes, sir. And I have a question. We are in three-dimensional space, X, Y, Z. Our Earth compresses it in all directions when it is moving in this space. But when the gravitational waves close nearby, it's a space-time two itself collide or anything. Is there any special relativity happening there?
The special relativity, meaning there's a wave that is going by, and there is a kind of a squeezing. If you think about it, it's due to gravity-induced relativity, whatever you call special relativity or not.
I'm asking question in a general relativity with special relativity, because the Earth squeezing with general relativity, and the space gravitational waves also coming, and it interacts with the space-time itself.
Yeah.
So those two space-time squeezes there.
So I think there's a total, if you think of, I mean, suppose a gravitational wave is going through Earth, for example.
Yes.
You're saying there's a contribution from gravitational waves which will be distorting,
Yes.
and there'll be some other kind of thing also. What we measure is the gravitational wave part, which is due to this thing, not due to any other one. So when you say relativity, special relativity deforming Earth, what do you have in mind? Is it you're talking about the tides or something, or what is?
So it's a relativistically I'm asking about. We define some signals, right? Is there any distortion from those interactions? I'm asking. If our calculations are right or wrong, I'm asking. You were saying we may be right, maybe wrong.
So I think,
what if I'm asking?
Yeah, correct. I think you're asking if there are additional corrections. So LIGO is situated in one side on Earth, right?
Okay,
and we are like a 4 kilometer by 4 kilometer arm length.
Yes,
so whatever will immediately concern our measurement is something which happens in that neighborhood.
Yes, sir.
So beyond that, anything, any other thing. See, if you want some effect to directly interfere, it has to be something which has a component in this frequency thing or something.
Yes.
In which case we can impact it, but I cannot think of anything which will be relativistic and which will impact us. But
the disturbance caused by the gravitational waves, and we have the our space-time also disturbed, right? So these two disturbances.
The space-time, if you are talking about a space-time disturbance due to a passing gravitational wave, right?
Yes.
So and I agree with you that if a wave is going by, it will be disturbing the entire space-time around the Earth. Yes. But what we measure is the local component near the LIGO detector.
Okay, sir.
So other thing, we cannot measure because we are not sensitive.
Right.
That is what we are measuring.
Okay, sir.
And any other contribution to this thing is what we need to filter off. It can be due to kind of Earth, seismic motion or anything, but that we need to filter off. But what we are measuring is the local disturbance caused by a passing wave near the detector site is what we measure.
Okay, sir. What if we place the same setup in space?
Yeah, space will be, at least this kind of seismic thing and so on will be gone. But then there are other things. There can be sources which may be constantly emitting in that frequency band. For example, there are some non-sources which will be emitting. So instead of we'll be replacing our seismic noises with confusion noise from astrophysical sources, which need to control, but we need to understand how they are and kind of subtract it off. But that's what the LISA would do. That they need to deal with double wide dwarf sources, for example. It's a constant low frequency thing. It will be there's a constant background due to that. But it'll be another kind of sources, but not the seismic ones.
Okay, sir. Thank you, sir.
This question, 3 people. She's waiting. Ask this one, ask. This is YouTube.
Thank you. Sir, you've mentioned, okay. So, for example, there is one wave that is coming from a merging of an event, and there is another wave that is coming from a background radiation or some stochastic background wave. So, do they ever interfere?
No, so I think if you think about, gravitational waves are already weak. So the interference term, the kind of cross term between them will be extremely weak. That's not an issue. And to answer your question, suppose you're asking, suppose I have a compact binary source hitting, and at the same time we may be actually seeing a stochastic background. How do you separate them out, right? So that is simple, because this compact binary thing is a short duration transient whose properties we know, somewhat frequency dependent, so on. Stochastic background will have its own properties which are known. So the analysis of a stochastic background will be applied to that kind of frequency dependency, separating that out. And analysis of a compact binary, like a binary black hole, will be using those spectral features which will be separating this out. So that is not going to cause any. So the fact that we may be observing binary black holes in presence of a stochastic background doesn't alter either of the either of the measurement, and the interference between them is too weak to do any damage to us, because that's 10 to the minus 21. 10 to the minus 21 is going to be like the cross time is going to be that small.
But what if two merger waves?
So that is an important problem. So you can ask, suppose two binary black holes hit the detector at the same time. Okay, now or some which can be kind of overlapping. This is not an issue so far. We have been detecting things once a week, maybe once in a day is the best thing. But even then, our rate estimates for them will tell you that that is not a big kind of big issue. However, your problem is relevant for LISA, because LISA, I told you, will observe supermassive black holes. It will also observe nearby stellar mass black holes, and these are all 4-year-long data, right? So LISA will be seeing all these cells at the same time, and you have to do analysis of all of them, keeping all these transient meaning year-long sources. So what they do there is that they have a data analysis strategy called a global fit. They will be fitting the big fit to the data will contain or will account for different types of sources, separating them out. So that requires a different kind of analysis, which is we are not yet in that regime, but there'll be more applicable for the LISA-like sources, where we'll have a global fit containing various components to the fit and subcomponents, which will be separately extracting out these sources. But that's a very valid question. Thank you.
Thank you.
1 minute. Who is the next one? Please wait.
Good afternoon, sir.
Hi.
Thank you for the lecture. So my doubt is, I wanted to know where the mass was. So when the merger happens, the mass is converted into energy, which we see as a gravitational wave, right?
Yeah.
So I just wanted to know, where does this dissipated energy goes? Will it dissipate to nothing, or
No, so
reflected?
yeah.
Is there anything to do with the dark energy or something?
It has nothing to do with dark. So I think whatever is dissipated, a component of that is what is hitting the detector. Right? So there's a wave has got an energy. A component of the wave is hitting a detector, which is exactly the one fraction of the 3 solar mass that is lost. So what is lost is what we're detecting. So it's not going to kind of anything. Dark matter, dark energy, that is a different thing altogether. We can probe, for example, using gravitational waves, we can probe the dark matter content, dark energy content, and so on. But that is not a place where this energy is everywhere. I mean, it's coming towards us. Whatever is the energy that is passing through us, we are trapping them, and we are doing a measurement. But it's not going. I mean, this exactly because they are losing energy is why we are detecting them.
So the known matter in the universe is getting decreased by one of the way of gravitational wave.
Nothing is lost, right? I mean, it's all, and this. I mean, total energy is conserved. We are the energy is propagating to infinity, and
Reduced, right?
huh?
The mass is reduced, right? Total mass.
Yeah, but I think that total mass is converted to radiation. So the energy of the radiation is equivalent to 3 solar mass into c square. So it's just a conversion of rest mass energy to radiation. That's all. There's nothing is lost. Yeah, there's no. I mean, mass loss in the sense, the final mass is less, but that mass is less because there is radiation, which is what we are detecting. So there's a conservation of total energy which should be there. Otherwise, there's a problem.
Okay, thank
The next, yeah. Someone in last row. Yeah. Wait, 2 more. Next.
Good afternoon, sir.
Hi.
How do we predict the mass of remnant black hole after a merger?
Yeah, so that's why I'm saying not prediction. So what we do is that if you do calculations in Einstein's theory, there is so if you know the initial mass and spin, Einstein's theory will tell you what is the final mass. Okay, so if you split, so yeah, I think your thing is a bit. I can give you a detailed answer. So this thing from here onwards is only a function of the new black hole that is formed. So by performing analysis on the remnant black hole formed by the merger, we can get what is the total mass of the new black hole, and by performing analysis on the this part, we can infer what are the mass of the component things, and we can ask whether the M1 and M2, the component thing inferred from the first part, the early part, is it consistent with what is measured from the second part, and that is how we do it. So to do this one, we make use of Einstein's prediction, Einstein's theory predictions.
Okay, sir. Thank you.
Yeah.
Here. Okay.
Thank you, Mike.
Yes.
Hello, sir.
Hi.
What is the use of gravitational waves? Like, what is the need to understand the gravitational waves?
Ah.
Other GPS tracking from the satellites, how does it affect us in our daily lives?
Yeah, so I think GPS tracking TRG mentioned is about not gravitational waves. That is about the effect of GR itself, right? Because of the gravitational field, the clocks run differently due to in different gravitational fields, and that is why we said that if you do not account for the change in the rate of clock running, you'll be running into trouble. Now, in terms of gravitational waves and utility, existingly we know we can only use it to infer astrophysical objects. There is nothing in routine life as such. I mean, it does affect my routine life because I'm paid to do this research, and that way it impacts. But other than that, we cannot use it for any telecommunication purpose and so on, because I told you terrestrial waves are extremely weak to detect. But in the future, we don't know. I don't want to close the thing on the future, what will happen. But right now, there is no day-to-day thing, applications of gravitational waves in day-to-day life.
Sir, nowadays, what the signal we are receiving from the space, we cannot get the exact or correct signal because of the space pollution. So how LIGO will overcome and what are the challenges they are facing?
What is space pollution?
Yeah, a lot of satellites.
Space pollution.
Space.
Yeah, you're asking about the effect of space debris on gravitational wave detection?
Yes, sir.
Yeah, I mean, that is not, LIGO-like detector, what matters for LIGO is about the mass of this debris. And if the mass is not a compact object, your satellite is not a compact object, we don't care. But I think your thing will be more important for LISA. For example, when a space-based mission, if you have, if you're hit by some asteroid and some random thing, it may be an issue, but it doesn't.
Is very low.
Yeah, I think even the debris are like everywhere. It will increase now. I think right now we are not still in a regime where it is going to impact our measurement of any type. But in principle, yeah, it's more applicable for the space-based one. And LIGO wouldn't care about the satellites until you make a very some kind of really hack into our system and make a satellite that will screw us up.
Okay.
So thank you for a wonderful talk, sir. I have two questions.
Yes.
One is you mentioned about this quadrupolar and octopolar. So that is initially predicted by Einstein theory. How we verify experimentally? Is it, for example, by seeing the wave, can we verify that is it octopolar or quadrupolar?
Yeah. So I think what happens if so again, Einstein's theory would predict all of them in kind of so the leading contribution will be quadrupole with subdominant octopole, hexadecapole, and so on. What happens is that when only quadrupole is there, the emission of radiation is at twice. So there's an orbital frequency of this thing, right? So the emission in the quadrupolar approximation is at twice that frequency, twice orbital frequency. Octopole would mean it is 3 times that, and hexadecapole would mean 4 times that. So by confirming that there are emissions at one frequency, twice f, thrice f, 4 times f is how we detect. So I don't have a picture yet. You can see a big peak at 2f, at a small peak at 3f, and that small peak is what I meant by octopole. Harmonics. So different harmonics of the orbital frequency.
So my second question is how we have a perspective about this gravitational waves from the thermodynamics perspective. Like we attach a concept of temperature to radiation, radiation.
Yeah.
Likewise, can we think of some kind of temperature to gravitational waves, or how this when we talk about gravitational wave the merging of two black holes,
Yes.
how the thermodynamics of it?
Yeah. So I think you can. So I think, for example, according to thermodynamical thing, entropy of two things will increase, right? You expect that the entropy of the initial binary black hole and the final black hole, it should have increased, which we can correct. So I think the fact that we are seeing an initial configuration comprising of two black holes and a final configuration comprising only one black hole, you expect area or entropy to increase according to thermodynamical notion, which we can confirm. So see, thermodynamics is giving you a viewpoint into the thing. We can view it from any point of view, but for theoretical calculation, you don't care which viewpoint you do. Sometimes you're right that thermodynamical perspectives can help you solve certain theoretical things. But to answer your question, we can confirm, for example, that the area or the entropy of the initial black hole and the final black hole obeys what the thermodynamical laws of Hawking, for example.
So can we attach the concept of temperature to this gravitational waves?
You can in a vague sense, but that is not much of any use. I mean, yeah. So I mean, if you use a background, for example, CMB and so on, it may make some sense to talk about what is the background temperature. Otherwise, there is no objective served by attaching temperature. But thermodynamics, I agree with you that if you can think of binary black hole problem to be a thermodynamic problem where area increases and so on, which we can confirm by using gravitational waves.
Nice, thank you.
All right, let us wind up. I would like to share an interesting thing. So when I think of having a lecture on gravitational wave, I contacted another gentleman. He's Satish Kumar Saravanan, who is working on LISA experiment. And he was in Brazil and he came to Salem. He's right now in Salem. I was inviting him for a talk. He says that, oh, you come to 93 lecture, I'm going to do 100th lecture. I want to do the 100th lecture. Anyway, I don't know. He's going to be here on 100th lecture and we are going to invite him. I don't know. But anyway, it's an interesting thing. Yeah? Inshallah. So I would like to remind you again, become a member of Tamil Nadu Science Forum and become the member of the WhatsApp group, Telegram group, and you can also subscribe to our YouTube channel, all those things, which we have circulated through the
LIGO in space.
QR code. Please become a member. That's my final reminder, request. So with this, let me thank Dr.
Thank you so much.
K.G.Arun. He gave a wonderful lecture and it was very live and really it's a beautiful lecture. And I thank you for accepting our invitation and he initiated